Okay, this is NMath A, and the next big subject is going to be vector calculus. So before I get into the calculus of it, let me just review vectors. If you're watching my videos, you're probably fairly familiar with vectors. When I taught this course, my students were fairly familiar with vectors. So I'm going to go through it quickly, but I do want to go through it. And the first part I'm going to do by I didn't even bother making slides like I usually do. I'm just going to go directly from my notes to get to the basic definitions of things. And by the way, my notes are generally, well, they're more extensive than my slides. And they're available for any of the subjects I cover in my videos. And if you want this one or any of them, just email me and I'll email you back the copy or copies. So let me go through this very upfront part on vector definitions and things. And here I'm talking about geometric vectors. The word vector can mean lots of things, but especially a two-dimensional vector I can draw on a piece of paper. We call this arrowhead where it's pointing the head, and this other end is the tail. What defines a vector is simply that it has a certain magnitude and direction. Those terms imply a frame of reference, and magnitude just means length, and direction. We say two, by the way, it doesn't have a particular location. It's free floating. All it has is magnitude and direction. We say two vectors are equal if they have the same magnitude and direction. They don't have to be in the same place. If all you do to get from one vector to another is scale its length, then you call that a scalar multiple of that vector, and those two vectors are parallel. So like these two vectors are parallel, and in fact, even if it's in the exact opposite direction, you could think of that as you multiply the magnitude by something negative. These two here are still considered parallel. We have a way to define addition of vectors geometrically. You could place B's tail at A's head. This resulting vector geometrically is the sum of those two vectors. Use the parallelogram approach. Go about defining subtraction the same way geometrically. But here's kind of a beautiful thing. I said there's a frame of reference, right? If we give that a definition, we'll call it the X and Y frame of reference. And I can, instead of direction and magnitude, I can give it two components. A component in the X direction and a component in the Y direction. And those two numbers convey the same information as magnitude and direction. So we just turn it from a geometric approach to an analytic approach. Now we can just describe a vector using two numbers, or a two-dimensional vector using two numbers. Three-dimensional vector using three numbers. By the way, a position vector does have a location. We always put a position vector's tail at the origin of our coordinate system. When we treat them analytically, all the things I described geometrically carry over. The quality means each of their components are equal. Their corresponding components are equal to each other. B1, the first component of B, equals A1, the first component of A, etc. Scalar multiple of a vector means you multiply each component of that vector by the same scalar multiple, scalar value. If two vectors are simply scalar multiples of each other, you call those guys parallel. And this is going to be the easy way to deal with parallelism. Two vectors are parallel if one's a scalar multiple of the other. Length is found by Pythagorean theorem. Addition, you just add the components. Subtraction, you just subtract the components. You don't have to draw pictures anymore. It might help to imagine what's going on, but we can do it all analytically. And as we move up to 3 dimensions, everything is very natural. Length is now 3 components, or Pythagorean theorem in 3 dimensions. And by the way, the words in this context anyway, length, magnitude, and norm all mean the same thing. Or generally, norm and magnitude might mean something else. But for us now, they all mean the same thing. A unit vector has a length of 1, by definition. You can normalize a vector by dividing it by its length or its norm. And the result is a unit vector, which means, like in this case, this u will be in the same direction as A, but its length will be 1. The standard basis, you've probably seen them, I, J, and K. I is in the X direction, J is in the Y, K is in the Z. And they are vectors. It's not just notation, they are vectors. And any general vector can be expressed as a linear combination of the standard basis vectors. So here's vector notation, and here is an actual linear combination of these 3 different vectors. I'll get in, by the time I get to the dot product, I'll go back to my slideshow mode, and we'll do that next.